Okay, we'll get started. So we were discussing solving problems using dynamic programming and solving dynamic problems using PMP. So let me remind you what the problem was. I wanted to minimize xt plus 1 equals to xt minus ut, and my j of u was minus log u0 minus log u1 minus log x2. So this was the terminal cost, this is the recurring cost, and we solved this problem using dynamic programming. So can someone remind me what the solution using dynamic programming was? What was my V2 of x2? We did it in the previous lecture.
So negative log of x2.
Negative log of x2. What about V1 of x1?
Negative 2 log x1 plus the constant.
Right, and V0 x0?
Was negative 3 log x0 plus the constant.
Wonderful. Thank you so much. And then did we compute mu0 star of x0? Mu0 star, I think it was minus x0 over, no, x0 over 3. And mu1 star of x1 was x1 over 2. Is that right? Does this look correct? Yeah, okay. What about PMP? I had P2 star equals to, was it minus 1 over x2 star? P0 star equals to P1 star equals to P2 star. And then U0 star equals to U1 star equals to x0 over 3. And x2 star equals to x0 over 3. Am I right? Okay, so x2 star is basically the state at time 2 under the optimal trajectory. So if we didn't have any perturbation in the system, this is what the solution looks like. What do you guys notice in this expression? So first thing that I notice is that the policy at time 0 is the same as my action at time 0 here. So mu0 star of x0 turns out to be x0 over 3 equals to u0 star. So it seems to me that dynamic programming and PMP, their solutions match at time 0. What about their solutions at time 1? What is mu1 star of x1? Let's look at x1 star. So if I were to apply this policy, what is my x1 star going to be? It's 2x0 over 3. So I'll have 1 over 2 times 2x0 over 3 equals x0 over 3, which seems to be equal to u1 star. Right? So one thing that I recognize here is that whether I use dynamic programming or whether I use PMP, I end up getting the same solution along the optimal trajectory. And it's very important to remember that we are getting the same solution along the optimal trajectory. Why would we not be on the optimal trajectory? Because of perturbations, right? So we've talked about it in the previous class. Real systems have perturbations. Perturbations can come because we have more people in the room than what we had anticipated. It could come because the wind is blowing in some different direction. It could come because there is just a gust of air, and after that the airflow died down. So variety of reasons why there are disturbances in the environment, and those disturbances are going to move us away from the optimal trajectory. So optimal trajectory is x naught. I mean, x naught is something that's given, but the optimal trajectory, whenever I say optimal trajectory, what I mean is x naught, x1 star, x2 star, xt plus 1 star. That's my optimal trajectory. So I can go off the optimal trajectory because of perturbations. One time, I'll give you another example of perturbation. So one time we were working on this cyber car, I think in Center for Automotive Research, you might have seen it. It was an ARPA-E project, and there was some mass of the vehicle that we had assumed in our computation, 2200 kilograms or something, I don't remember. But it just so happened that when we wanted to do the testing, the graduate student said it will be fun to drive the car together while it's driving autonomously on the road. So all 4 graduate students sat. The mass of the car became 2400 kilograms. Okay. So another reason, human reason, completely human reason, why the mass of the vehicle could change, as a result of which I'm no longer on the optimal trajectory that I had computed. The good thing was we were using dynamic programming to compute the solution. So it automatically uh, got us onto the optimal trajectory for the new mass of the vehicle. But anyway, so that's just a tidbit of information. So there are variety of reasons why you would not be on the optimal trajectory. Okay, so long story short, DP and PMP computes the same action, optimal action, as long as we are on the optimal trajectory. Now let's look at another expression. I want to look at what is gradient of x2 of v2 at x2 star. So v2 of x2 is minus log of x2. So gradient with respect to x2 is minus 1 over x2, and I'm evaluating it at x2 star. Do we notice something between the solution for PMP and this gradient? What is this equal to? V2 star. What about gradient of x1 of v1 of x1 star? So v1 of x1 is minus 2 log x1 plus constant. The gradient of constant is 0. So this is minus 2 over x1 star. What is x1 star? X1 star is 2x naught over 3. So this is minus 3 over x naught. What is P1 star? P1 star is minus 1 over x2 star, so that is minus 3 over x naught. So this is the same as P1 star. And the same thing happens for V0 as well. So along the optimal trajectory, the gradient of the value function we found through dp is the same as the co-state vectors of the optimal solution we found from PMP. And remember, there's another viewpoint, which is we can derive the same PMP expression by treating it as Lagrange multiplier problem, like as a constraint optimization problem. And there P0, P1, P2 star was Lagrange multiplier, right? Is it a news that the gradient of the optimal value is equal to the Lagrange multiplier? Right? So remember sensitivity theorem, we talked about sensitivity theorem where the gradient of the value turns out to be the same as, I mean, it's actually negative of Lagrange multiplier in that case, but in this case, because of the way we have defined things, it's actually equal to P2 of x star, P2 star. Yeah, perfect. What is gradient of x of Vt? What is gradient of xt of Vt? This is the sensitivity of optimal future cost to go for small perturbations in x2, in xt, sorry. And as we said, the perturbations could come because of noise in the system, and so the co-state vectors are essentially measuring the sensitivity of the total cost, the future cost to go along the optimal trajectory for small perturbations in x2. So all of this is connected. I just wanted to show you the connection through a real example without going through a burdensome proof. But essentially, in all cases, if you are solving a problem using PMP versus if you are solving the problem using DP, you will always have this relationship that along the optimal trajectory, the sensitivity of the value function is the same as the co-state vector at that particular point of time. Okay. Any questions so far? Okay. Awesome. What else have we talked about it? So we've said that PMP, computing the optimal solution using backpropagation, is computationally much cheaper than to solve this problem and compute the value functions at every point of time. So if you want to execute this on a hardware, it might take you 5 seconds. Executing this might take you only 50 milliseconds, okay, on the same hardware. So this one is really complex, this one is really simple. And so depending on the situation and depending on the microcontroller and depending on a lot of other factors, you might pick this algorithm over this. So what are the conditions where PMP makes sense and DP doesn't make sense? If you have computational bottleneck, if your environment doesn't change that significantly in short duration, for the duration in which you are actually solving the problem. So remember, we are only solving the problem from time 0 to t plus 1 star. So if each t is 100 milliseconds and this capital T is 10, then we are only looking at 1 second worth of trajectory. What are the applications where things don't change in 1 second? A lot of applications. Okay. So there, if you're only optimizing over the next 1 second, I don't know why one would want to optimize things over 1 second, but if you're optimizing over 1 second and things are not going to change in 1 second, you will use PMP. So let's think of some examples where, or if you're computationally bottlenecked. So let's look at it. 3551. How many of you have taken 3551? Okay, a few of you have taken 35. Feedback control systems. Maybe there is a corresponding course in mechanical engineering that some people might have taken. So people have done control system design using Bode plot, Nyquist plot, and all that stuff that we teach in those courses. There you are not optimizing any cost, you are just meeting some requirements, and you want to use those algorithms where the system dynamics is so fast that you don't even have time to compute. So if I turn on the switch here, immediately this additional 100 watt of power needs to be supplied to this particular bulb instantly. All of this information through the electrical grid goes to some generator somewhere in Ohio, and it says, okay, we need to generate 100 watts extra energy because somebody is requesting power. in OSU campus. So you use PID controllers, lead lag compensators, things like that. We have a car engine. What's the RPM of typical car engine? 1,000, 2,000, 3,000, something like that, depending on where you are driving. And you don't have the time, you don't have the bandwidth and time to figure out how to, like, to do some optimization at that particular time scale. So you end up using lead lag compensator, Bode plot, whatever, and then figure out how to control the system, what the U should look like as a function of X, right? So that's 3551. Then we talked about, then you came to 5500, and now I'm saying that, look, there are problems where there is a time scale, and in that time scale you can do the optimization. So I'm in a building, I want to optimize the air conditioning of the building over a day long period. And in a day long period, a lot of things will change. So some people will come and sit in the class. So right now we are sitting in the class. We are emitting a lot of heat into the air conditioning, into this environment, and the air conditioning system is supposed to take that heat and reject it to outside. And if and so I can potentially optimize it. But then what's the time scale at which things change inside the class? So this class is going to go for 55 minutes, and then there'll be a recess for 15 minutes, and then there'll be another class for 55 minutes, and so on and so forth. So things are not going to change in 55 minutes. I'm assuming you guys are not going to just leave the classroom in the next 55 minutes, so things are not going to change. So there, you can safely use PMP. Okay, the air conditioning system is working every second or every minute. It's making some decision, and since nothing is going to change for the next 55 minutes, you can use PMP to make a decision. But if you're looking at a time scale of an entire day, you have enough computational power within the building. You can keep a big computer, and then you can optimize the energy consumption using DP, because you will have things changing over time. You will have the weather is changing, the number of people are changing, a lot of things are changing inside the building over a 24-hour period, and so you can use dynamic programming to solve problems of that type. So really, it depends which algorithm you pick, whether you use PID controllers or whether you use PMP. So PID is extremely cheap. You can build hardware that can execute PID within a matter of microseconds. So you use PID in electrical machines and all that stuff, like motors and whatnot. So that's very fast. Then you have PMP. It works in the matter of milliseconds. You can apply this algorithm in milliseconds. Then you have DP. You have to apply this wherever you have. You can apply this in millisecond scale. Like for instance, in the autonomous driving scenarios, you're trying to compute the solution every few milliseconds. And what can we put on autonomous cars in order to compute this complicated optimization problem every few milliseconds? We put a GPU on it. We put a CPU on it, like some complicated 10-core CPU is put on a vehicle to be able to compute the solution. Nowadays, the humanoid robotics is the craze. A lot of companies are building humanoid robots, especially in Bay Area. And then in those cases, again, they have CPU and they have GPU actually in their heart area. So they put the battery and the GPU and the CPU in this particular area of the robot, and they are running dynamic programming in order to compute solutions. But if you look at the actuators, it's quite likely that they are using PMP to compute the actuation signal. So the bigger level planning is happening through DP, the smaller level actuation is happening through PMP, and even smaller level actuation, which is the controls on the motors of the joints and stuff, that's happening through PID controllers. Okay, because you don't have enough computational capability there to be able to do some complicated optimization. And perhaps complicated optimization is not really needed at that particular time scale. Okay, perfect. So is it clear why we should use PMP versus DP versus PID, right? So I think that's easy to understand. Okay, the second part, so we have talked about this. Oh yeah, so we need to talk about time consistency. Oh, one more thing that I wanted to point out. PMP is giving us open loop control. So U1 star is not a function of X1, it's just a function of X0. So everything is determined by the value of X0. Once you know x naught, everything else gets determined. So what you get is an open loop control, because control is not a function of state. What you get here is a closed loop control, because control is a function of state. Okay, so that's one major difference between PMP and DP, and this is something that you will have to write in assignment 6. So let's talk about time consistency. So what's this notion of time consistency? So one notion of time consistency that we have talked about so far is the fact that if you are along the optimal trajectory, the solution that you get from PMP is optimal along that trajectory. So that's called weakly time consistent. This is strongly time consistent, because even if you perturb your state by a small amount or even by a large amount, you know that the policy is optimal no matter at what state you are in. So essentially you get what is known as a strongly time consistent solution. So even if you perturb the trajectory, you have the optimal solution moving forward. What is time inconsistency? Okay, so what is time inconsistent behavior? So let me ask you a simple question, and hopefully that will tell you what is time inconsistent behavior. So how many of you have eaten the cake with the expectation of going to the gym next day and have not gone to the gym? So I'm definitely one big example of that. But how many of you have done it in the past? Which is, I'll do X and then I will do Y, and you do X in anticipation of doing Y, but then you don't do Y. Okay, almost all of us have gone through that period of life when we had to do that. And that's a time inconsistent policy. So your policy was, I'll do X, then I'll do Y. That's your policy. That's the optimal policy today at this point of time. And then you finished X, that's the next state. And now you are supposed to execute Y, and you didn't execute Y. So for some reason, the optimization that you solved after completing X turns out to have Y as a suboptimal solution, and therefore you didn't have to do Y. So that's called time inconsistency. So humans are extremely time inconsistent. So we want our autonomous vehicles to be time consistent, but we ourselves are extremely time inconsistent people. Okay, so what's time consistency? So let me define weakly time consistent. So U naught star to UT star is weakly time consistent if UT star to UT star is optimal for cost to go at time t, given that the state trajectory was x naught x1 star to xt star. Strongly time consistent mu naught star to mu t star is strongly time consistent I should use if and only if mu t star to mu t star is optimal Okay, so those are the three definitions: weakly time consistent, strongly time consistent, and not time consistent or time inconsistent. Okay.
Let's say
Yes.
I need to solve problem number one and then problem number two. Okay,
Yes.
this is the optimization algorithm that I have,
Mhm.
and then or the steps I have.
Mhm.
And I solve problem number one, and then now I'm in the process of solving problem two, but some interrupt happens. I don't know, like I got sick and I need to run to
Right.
hospital, for example.
Right.
Okay,
Right.
so like,
So
because of
that's still strongly time consistent, because even if you have not been on the optimal trajectory so far, the rest of the policy is still optimal for the cost to go. So in that particular case, like if you're saying that because you got sick, therefore you didn't go to the gym, it means that your XT is different. XT is sick, and your optimal policy mu T star of XT is if you are sick, don't go to the gym, and if you are not sick, then go to the gym. So your mu T star hasn't changed. Your action might have changed, but your policy has not changed. And what I'm really saying here is that your policy itself has changed.
state change or the dynamic.
No, so I'm assuming that so far you are. So in this case, I'm assuming that you are on the optimal trajectory. In this case, I'm assuming that you are not on the optimal trajectory, and yet your policy has not changed at all for the cost to go at time t. And this one, not time consistent. Well, you can be not time consistent for this, or you can be not time consistent for policy also. So it really depends. It really depends on what kind of problem you are trying to solve. So we'll see some example of this. But what this is essentially saying is you have a policy where as soon as you arrive at that time period, you essentially end up changing the policy. You change the entire policy itself. You're not changing your action. You're just changing the complete policy moving forward. Okay. So what is the reason for time inconsistent behavior in human beings? So, the reason why I'm telling you this is if you are going to Wall Street, this is something you have to deal with on a daily basis. Okay. Or if you go to business school, or if you go to finance, or if you go to some other areas outside of like electrical engineering or mechanical engineering, you are going to deal with people, and people are time inconsistent. So, you will have to deal with it. But as long as you are working on electrical machines and you are working on humanoid robots, you will be in these two situations. So I want to ask you, the question that I really want to ask you is, why exactly do we have non-time consistent behavior in human beings? What happens to our objective function when we are solving the objective function? What happens which leads to time inconsistent behavior?
I think the problem is changing. Is that correct?
Okay, definitely the problem can change. So for instance, you started with the state transition function of this, and then the state transition function changed for whatever reason. That can happen. So in the case of, let's say you are driving a vehicle and the vehicle breaks down, some brake has failed or whatever, right? So now your transition kernel, sorry, the state transition function itself has changed, and you are certainly not time consistent anymore because your transition kernel itself has changed. Yeah.
Like for the scheduling problem, like if you're putting like workers on planes to fly them and one of them gets fired or let go, then you can no longer, send them to the.
That's, yeah, definitely. Right. So, for instance, yeah, that was not even part of your state space that the worker will get fired. So, you didn't assume within your state description that the worker will be fired. And so, if the worker gets fired, now you are in a completely different transition setting. And so, yeah, certainly that could lead to. So, in both these cases, the transition kernel itself is changing over time, as a result of which your policies are no longer time consistent, for sure. Anything else that comes to the mind? Yeah.
Could it maybe be a
perturbation of like you have the motivation now, you know, if you eat the cake and then you're gonna go to the gym, but you no longer have the motivation when you go to.
Yeah, after eating a cake, you probably won't have that motivation for sure. But how does that motivation comes into the picture? So we are solving an optimization, right? So where does motivation appear in the optimization problem?
Well, you have to be motivated to go to the gym, so you think you will have the motivation.
Right, but is it part of the objective function or is it part of the state transition?
State transition?
Actually, that's part of the objective function. Yeah. So what ends up happening is your cost function itself has changed moving forward. So after you ate the cake, your cost function has changed moving forward. Yeah.
I think from rational, it's the partial observability of the
Yeah, so we are not assuming the partial observability here. So right now we are looking at completely observable. So everybody can look at the state completely.
Oh.
Yeah.
Okay.
Yeah.
And I think it's both like rational and irrational because human beings are.
That's right. Yeah. So non-type consistent behavior comes from the irrationality. Yeah.
Also, I think one of the reasons that you cannot follow the schedule is that you are now capable.
You are?
You're now capable. You're now able to do that. For example, if you're sick, your body conditions do not allow you to.
Right. But the sickness is part of the state, XT. So you'll have like multiple states in your brain. So one part is sickness, the other part is feeling happy, the other part is something else. And yeah. So, you know, one of the things that, so economists have thought a lot, people from economics department and people from business school, they have thought a lot about this not time consistent behavior. And so one thing that I want to cover, so it's a very big field. I don't want to cover everything in the field and it's not really relevant to our course. But one thing that they have talked about, and that's something I've given you as an assignment, is when you have what is known as hyperbolic discounting in the objective function. So you know, you are at every point of time, we are trying to optimize the cost to go. So initially, my cost to go was J of u, which is Ct plus 1 xt plus 1 plus summation t equals 0 to capital T Ct xt ut. That was the initial problem that I started with. But then at time t, my cost to go function is Ct xt ut plus alpha times summation k equals t plus 1 to t ck xk uk plus ct plus 1 xt plus 1. And this alpha is between 0 and 1. And this is known as hyperbolic discounting. Maybe I'll make it closed interval 0 to 1. Well, maybe not. 1 may not be included. So this is just one classical theory. So at every point of time, the idea is that we as human decision makers are trying to optimize this sort of a cost function, okay, where alpha is our hyperbolic discounting factor. And so when we are posed with this problem statement that I'm going to eat the cake now, that's the optimal solution, and in the future I'm going to go to the gym. The thing is that the effort that is needed to go to the gym is being discounted by a factor of alpha, and that alpha could be very small. It could be between 0 and 1. So right now you are thinking that after eating the cake at time t, I'll have a lot of motivation to go to the gym. But then when you are solving the optimization, you are multiplying this future motivation by a factor of alpha. When the time comes, when you are at time t plus 1, you are solving this optimization problem, Ct plus 1 xt plus 1 ut plus 1 plus alpha summation t plus 2 to capital T plus Ct plus 1. So now you're looking at all the effort that is needed to get to the gym. I have to pack everything in the car, I have to drop off the car at the parking lot, I have to walk to the gym, then I have to go inside the gym, change, and then I get to start running. And that has happened with me a lot of times. So I totally understand and feel that emotion. And so I'm like, it's too cold, forget it. I'm not going to go do all this stuff. Let's just move on to the next task. Okay. So initially, remember, this cost was being multiplied by alpha. It's no longer being multiplied by alpha here. Okay. And that's why if you solve this problem, you get a policy. You solve this problem, you get something completely different policy. And that leads to a time inconsistent behavior. So in your assignment, I have given you this notion of hyperbolic discounting, and I have asked you to use DP to solve this problem. Exactly this problem, okay, for 2 or 3 time steps. And then what you have to show is that the optimal policy you get here is different from the optimal policy you get here, which is different from the optimal policy you get here. And that explains why we have time inconsistent policies in certain settings. But this is just a very fascinating theory. So I deal a lot with problems of this type in my research, but certainly not it's not part of this course, so I don't want to go deeper into it. Yes.
What about the past cost, like memory? Does it also take place in the past?
So the idea in all dynamic systems is that the memory is compressed into the state.
Oh,
So whatever things you need to remember from the past, you compress it into the state and you present the state.
oh,
Okay. So I'll give you an example. This room, I'm assuming this building was created in 1960. The temperature of this room at 1960 was something. At the time the building was first opened and the air conditioning system was first turned on, there was some temperature of the building. But if I want to control the temperature today, I don't need to know the entire history of temperature of the building since 1960 when this building was first commissioned. Right? So I've compressed the entire history into just a single variable, which is the temperature, the current temperature of this room. That's it. And I can forget everything that has happened since 1960 until today. Okay. There are certain cases like the healthcare problems where the long-term history is important. So if you fell down from a bus when you were 15 years ago, when you were 15 years of age, you will have the back pain when you are 50 years of age, right? So that problem, that memory will be there in the body that, look, you had an accident long time ago, and so you will have the pain for the rest of your life. Or if you have consumed tobacco or something, then the risk of the cancer will go up throughout your life. It's not like today you are consuming tobacco, so the risk of cancer is high today, but tomorrow if you stop doing it, the risk will go down. The risk will go down to zero. That risk will continue to remain. So anyway, there are situations where there is a long-term memory. There are situations where there is zero memory, like the temperature control, zero memory. I don't need to know what happened in the past. Today's temperature is all that I need to know to optimally control the temperature of the building. So all of this is extremely fascinating subject, and of course, something that I do as part of my research, which is dynamic optimization. So I have to think about it. Sorry? Time delay systems are another ones where there is a lot of memory. So time delay system is something like, if you think about the air conditioning system here, it's not like the cold air is getting generated here, or hot air, whatever is coming in, is not getting generated here. It might be getting generated somewhere else. And then from there, the air is traveling and coming into this room. So there is that memory as well that one needs to take into account when solving problems of this type. Any other question? Okay, perfect. So, now for the rest of the semester, we are going to talk about various Okay, so this problem is easy to solve. We've all agreed that, and so this one we don't want to talk more about it. It's just the basic gradient descent algorithm being applied, and we know all about how to apply gradient descent algorithms. DP, on the other hand, is an extremely important topic, dynamic programming, and being able to compute the mu0 star, mu1 star, v0, v1, v2, all of this is extremely important. But as we mentioned, you have to solve infinite number of optimization problems at every point of time, and that has to be done t plus 1 times. So that's an extremely computationally expensive affair. So how do we simplify the computation of DP? Especially when we are looking at extremely long horizon problems. So I want to go to Mars, I want to go to Moon, or I want to drive my vehicle from here to San Francisco, right, over a 4-year, 5-year long day. How do we do the DP for those kind of settings, right? So we have to do planning, we have to execute that plan, and things will change. When I'm going to my home, somebody will come and merge in front of me, somebody will go out of my lane, and so on and so forth. So things are going to change, and I have to keep planning and replanning and replanning and replanning. And I know that whenever something like that happens, I cannot really use PMP because it gives me an open loop solution. I don't like open loop solution. I like closed loop solution where I'm using sensors to infer the X naught. So I have temperature sensor in this room that's inferring the temperature here. I have fire sensor. Oh, we don't have a fire sensor here. Amazing. No, we have one. Yeah, okay. So right here next to the projector, we have a smoke sensor. So we have a smoke sensor in this room to measure the state of smoke in this particular room, right? So we have sensors to measure all this state. And now I want to make use of that information that I'm getting from my sensor to figure out what the optimal policy, what the optimal action on the basis of my reading should be. So this whole area is studied under the umbrella of what is known as approximate dynamic programming. Okay, so true dynamic programming is very complicated. I have to do this. If I have to go to Mars, that's a 9-month long dynamic program that I need to solve at every 100 millisecond interval. Too complicated. So let's talk about approximate DP. So in approximate DP, my problem remains the same. I have the same problem. This is the original DP problem that I was given. I'm going to Mars. My capital T is 1 billion. I have 1 billion cost functions. I have a terminal cost function. What's the terminal cost function if I'm going to Mars? My state should be on Mars. My position should be on Mars. It shouldn't be on some random place. In fact, when you're going to Mars, you want to be within 100 meters of the location where you wanted to go on Mars. So it's not like you can be anywhere in the Mars and you are happy. I mean, that was the success in 1970s, but not anymore. So now I want to go to this particular location in Mars because I want to figure out what the soil looks like, whether there was life on that particular location or not. And I want to be within 100 meters or 200 meters or 1 kilometers of that particular location on the surface. So that's my terminal cost. And then I have a running cost, which is a fuel cost that I have to spend to get there. So the problems with DP, T is very large. Well, not T is very large, but T can be large. FT and CT could be complicated. How to store Vt and μt for every T. Okay, so let's go back to 1970s. So we are sitting in 1970 in this room, and somebody came and told us, look, this is the problem we want to solve. There is this new theory called dynamic programming, which was discovered in 1950, so just 20 years ago. And the problem is I'm not able to use this new technique, even though my system is dynamically changing because I'm going to Mars, my mass is changing, there is wind gusts in the air and whatnot. So I want to be able to use dynamic programming, but I'm facing all of these difficult challenges. What would you do? How would you advise the US government on how to go to the moon? Well, actually, in 1970, they already reached moon. Okay, 1968, I'm going to change the year. So we are in 1968, and this is the problem that needs to be solved. And remember that in Apollo mission, the processor that was on board was much smaller than the processor we have in our phones today. So you have to execute whatever algorithm you come up with, it has to be executed on that particular microprocessor. Think about it, and let's try to brainstorm some ideas.
Can we fake it?
Can we? Yeah, we are not in 1968, so we are already faking it. But okay, what's your suggestion? Yeah.
I think we can apply PMP first, and in that way we'll have the optimal trajectory and also the first order approximation of the optimal trajectory.
Okay. Good idea. Okay, so I use PMP for what? For the entire 1 billion,
Yeah.
for the 1 billion time step problem. You want to use PMP? Okay, that's very bold of you. I like I like that idea. On a 1968 computer, right? You want to do PMP on a 1 billion dimensional problem. Okay. No, I think it's not something to laugh about. We can come up with very complicated ideas, and then we'll try to figure out how to simplify it. So what else? What other idea do you have? Anything else?
Moving horizon type of approach maybe.
Moving horizon. That's a good idea. So what is moving horizon?
So let's say we have 100 steps to think about.
Uh-huh.
Let's not think about 100 steps. Instead, think about 10 steps.
10 steps.
Do the best, and then even
Awesome.
in the next step,
Uh-huh.
again, like one more time like this.
Yeah.
Then ahead for the next 10 steps, and then.
Amazing. Very good idea. So the idea is, let's talk about moving horizon. So we'll optimize for the next 10 steps, and then we'll optimize for the next 10 steps, then we'll optimize for the next 10 steps, and so on. So my running cost, my terminal cost is I need to reach Mars. Okay. Otherwise, I get infinity cost. If I don't reach Mars, I have infinity cost. My running cost is I need to save fuel. I'm only considering the next 10 steps. What would save fuel in the next 10 steps? Not fire the rocket at all. You get the best fuel economy by not firing the rocket. But does that really achieve our goal? So how do we fix that? It's a good idea. It's a good idea. I want to make sure that this T is as small as possible, hopefully 10. I can execute a 10-step dynamic program or 10-step PMP on a microcontroller of 1968. But the problem is that I can't really truncate the cost and not consider what's going to happen in the future. That's a problem.
We can change the cost function.
Okay, perfect. So what do you want to do?
Instead of just save fuel, we can also say that maybe like we are trying to go to San Francisco.
Mm-hmm.
We are here in Columbus.
Yeah, we are here in Columbus.
In the next 3 hours, we need to be somewhere close to Cincinnati, for example, like that type of.
Okay. Good idea. So I want to solve the optimization from here to Indianapolis, and I say that in 2 hours I should be at Indianapolis. So in some sense, I have the running cost for the next 10 time steps, but then I add a terminal cost which says that, look, I don't want to be in San Francisco at time 2 hours, but I want to be at Indianapolis at time 2 hours. Amazing. So that is that particular algorithm. There are two types of algorithm. One is known as rollout algorithm, and the other one is known as MPC, model predictive control. So we'll talk about those algorithms. That definitely solves problem number one, where T is extremely large. So MPC and rollout algorithms are two different algorithms used for solving problems where T is extremely large, and you have a non-trivial terminal cost. Okay, non-trivial terminal cost. You can have a trivial terminal cost. Like I want to minimize energy, and then nothing. CT plus 1 is 0. Like I'm trying to optimize the building's energy cost from morning till evening, and then in the evening I don't care what happens next day. Like it's terminal cost is 0. So in that case, I can just pick the running cost and forget about. I mean, we should probably not forget about the future, but in some cases you can forget about the future. But certainly when you have non-trivial terminal cost or non-trivial running cost, then and T is very large, then rollout and MPC are two different algorithms. What about this? FT and CT is very complicated. So I'm building a rocket, I'm sending a rocket to Mars. There are 500 things happening inside that rocket. My FT is very complicated, my CT is very complicated. What should I do? I'm especially looking for ideas from people who work at Center for Automotive Research.
Maybe break it down into like several different like main modules. As long as the main modules they have like
Awesome.
specific features that
Yeah.
counters like happens. It's okay.
Okay, so how do you know what is the main module and what is not the main module? So I'm driving a car. Okay, so I'm assuming everyone here drives a car or drives some sort of vehicle. So your engine is running at 1000 RPM, and you are probably making a decision every 500 milliseconds or something like that. Okay, so how do you know what to ignore? What's the main module? What's the main module when you are driving the car? Our brain, right? That's the main module making all the decisions. What about the other lower level decisions that are happening inside the vehicle? We just ignore it, right? I don't care what the RPM of the engine is or what the air conditioning system of the engine is doing. I'm focusing purely on what's happening on the road and figuring out appropriate commands on the vehicle to make sure that the vehicle is driving safely. Awesome. So that's known as a singular perturbation theory. So it's studied under the umbrella of singular perturbation theory, and in that case, what you do is you have like the state which is extremely high dimensional, and you cut off some portion of state that is changing at a very fast rate, and you only pick the states that are changing slowly, and you do the dynamic programming for that particular set of states. So that's known as singular perturbation, where you break down the system into fast dynamics and slow dynamics, optimize the slow dynamics, don't optimize the fast dynamics. Just do a PID controller for the fast dynamics and move on with your life. So that's roughly how most of the systems are optimized in today's world. So you have a fast dynamics, slow dynamics, ignore the fast dynamics, design a PID controller, forget about it, just solve the slow dynamics problem using dynamic programming. And that way you reduce the dimension of XT that you are considering. So that deals with the complicated FT. What about complicated cost function? What do you do with complicated cost function?
Approximated, maybe.
Approximated. So you have a complicated cost function, but you can approximate it with a quadratic cost function or something like that. So instead of trying to optimize a very complicated cost function, you come up with some trajectory and do the tracking of that particular trajectory, right? So that's how the rockets are actually sent to space. So some physics guy, how many of you have seen this movie Hidden Figures? Right? I'm assuming many of you have seen, right? So what's that scientist doing? It's trying to figure out what the trajectory to the moon should look like. And once you figure out the trajectory, all you have to do is track. You don't have to worry about all the other stuff like complicated cost function that might happen. Just track the particular trajectory. So then you do the cost approximation. Awesome. What about storing VT and mu-T? So now I have done so my T was very large, and somebody said I need to use rollout algorithm. So I used rollout algorithm. My FT was very high dimensional state. I had a very high dimensional state. I did this singular perturbation thing. and I pick the most important. I'm so sorry. I'm overshooting. But anyway, so this one we have done. We have figured out that we do the singular perturbation and just consider the smaller set of states. For cost, we are just going to do tracking or do some cost function approximation. In the next class, I want to think about how do we store Vt and mu t at every point of time. So we have a 10-step problem with a quadratic cost and some complicated or rather simplified transition function. How do I store Vt and mu t on a computer? Because I need to store it in a microprocessor in order to be able to execute the policy. So think about it, and we'll talk about it on Monday. Thank you.